Minimum time to reach the last room. There's a dungeon with n by n rooms arranged as a grid. You're given a 2D array move time of size n by n, where move times ij represents the minimum time in seconds when you start moving to that room. You start from room 0, 0, and at time 0, you can move to an adjacent room. Moving between adjacent rooms takes exactly 1 second. Return minimum time to reach the last room, n-1, n-1. Two rooms are adjacent, they share a common wall. Okay, so represents the minimum time in seconds when you can start moving to that room. Okay, so it's a 2 by 2, and you can move from the starting room to one of the adjacent rooms, the 4 or the 4. This is to the right, this is to the south. In 1 second, so you're reaching those rooms. Time 4, you move from zoom. Okay, so you can move at time 4, so you reach this at time 5, and then you reach this at time 6. So here, at time 0, so time 4, it takes 1 second to go to the next room. So time 0 opens, so it takes 1 second to go here, another second to go here, another second to go here. Time 1 takes a second to go here, so you actually get here at time 2, and then get here at time 2. Okay, I think this might be some sort of I think this is probably some sort of queue, like a breadth first search queue. So you want to go through all the rooms. Yeah, I think this might be use a queue to keep track of the the lowest time room. So lowest, keep track of the rooms with the lowest time cost to reach, starting with the initial room cost 0, adding to the queue for every neighbor. Wait, that's not a queue, that's going to be a heap, because you always want to use the lowest thing in the heap. What am I thinking of here? That's a heap. Okay, so for instance, if we start so say we have a heap, and the heap starts with our initial room, which is going to be room 0, 0, row 0, column 0, and time. So this is tuples is row, column, time. Actually, it needs to be time first, because it's going to sort by the first element of the heap. of the tuple. So time row column. And then for while heap exists, say time row column is equal to heap pop, top of the heap, and then for each neighbor, so I'm going to do a quick function for defining if it's a valid row column. Return if that row is less than the number of rows and the column is less than the number of columns, where rows is equal to the length of the list, the length of the move time list, and columns is equal to the length of the first row. Okay, so if this is a valid, no, actually, and I need another, generally when you go, the quickest way to iterate through the adjacent parts of a cardinal thing is you have a list of deltas. A list of deltas, so like 0, 1, 0, -1, 1, 0, -1, 0. So this is the change in row and change in columns. So for every DRDC in deltas, where DRDC is delta row, delta column, the new row, new column is a row plus dr, column plus dc, and if it's a valid adjacent position and no, if it's valid and we haven't seen it before, or this is we need to keep track of if this is a lower time cost to move to that spot. Is that how I want to think about it? So if you have a particular path to get to a particular room, so it's always going to pick, the heap is always going to guarantee that you look at the lowest cost time for the room, or the time, the next lowest room, the next room with the lowest cost. But it doesn't guarantee the next room with the lowest cost. Okay, let's go ahead and just assume that this is going to work out. And again, if it's a valid room, then interesting. So I think the time it takes to get to, let's say the next time to get to the room is either going to be 1 second after the room opens. So like for instance, if this is 4, then opens at, so you can get there at a low of 5, if it hasn't been opened. And if it's already been opened, then you get to it in the current time plus 1. So it's going to be the smaller. It's going to be at minimum the time of that spot. So move time of that spot, next row, next column, plus 1, or it's going to be the current time plus 1. And I think you would then add that to the heap. But you don't want to add redundant ones. I don't want to add redundant ones. Maybe I need a scene is a set of things of rooms that I've seen, and if this particular should be a set, I think maybe it should just be for efficiency. It should be a 2D array of false. False times the number of columns for k in the range of the number of rows. So I think that's right. Okay. Actually, let me double check this. Print scene turn 0. And let's do test case. Actually, that should be fine. Yeah, that's right. The sizing is correct there. Okay, so if I haven't seen something, so if the row is seen, if this row and column is true, then continue. Otherwise, say seen if this row and column is true. It's because when you add stuff to the heap, it might go across the same rooms. Because we're doing that for all the neighbors. Okay, if it's valid and seen at this row and column, if we haven't gone there before. Seen at this row and column is false. It does seem like I'm double checking seen here, but I think it's probably fine. It's probably the more Pythonic syntax. Next time is that, and then I'll do heap push onto the heap tuple that is the next time the row and column. And I also just need to check for the answer here. So if the row is equal to rows minus 1 and columns is equal to cols minus 1, return whatever the time is, because this is always going to give you the low. And this should otherwise return -1. It should never really get there. Okay, oops, I'm gonna remove this. Okay, definitely just always got there. Okay, so the heap is originally 0, 0, 0. So it's gonna go next time heap push. So it pushes. Let's go ahead and just print out the next heap after I do each iteration. Okay, so this is an adding thing. So DRDC. That seems fine. If it's valid. Oh, not seeing this row and column, this next row and this column. Okay. Interesting. This should be like 5, 0, 1, and 5, 1, 0. Oh, this should be the maximum, not the minimum. Okay. I think it should be the maximum. It should be, yeah, that's the maximum. So 5. Okay, that's correct. And then it's going to use 5, 0, 1, and then it's going to just do 6, 1, 1. That's correct. Uh, 6, 1, 1. Why doesn't this return? If row, oh my god. No, that's right. The number of rows is 2, right? Row is 1. Columns, oh, the column is columns. Oof. Okay. This is a little slow. Wonder if I can do something that's slightly faster than this speed. Do 37%. So for every row, I wonder if I can somehow prevent it from adding. So if I think maybe I can do the check for the exit right here within this spot. Is it possible? Because I'm always starting at the lowest room. And if I reach the ending room in this check, I think this is probably fine to do the check right here. If it's a valid room and not seen, So that would shortcut a lot, I think. Let me see here. If the next room is equal to rows minus 1 and the next column equal to columns minus 1, return the next time. Okay, yeah, that improved it. I think maybe I can get rid of this check. I think this might fail in like trivial case. But is a trivial case. How many rooms are there? Yeah, so there's no, it's not always, there's going to be at least a 2x2 row, 2x2 matrix. So I think I can get rid of the estimate right there. That should maybe shortcut a little bit of the speed. Okay, that didn't change it at all. That actually made it worse. Okay. Now, do I need should I be checking scene here or checking scene here? The first time I get to a particular room, is that just going to be the fastest? Yeah, maybe I can actually set the scene to be true here. Scene of next room, next column is true. And then that means that my initial room is never going to be a neighbor to itself, so therefore I should make the scene of 0, 0 to be true here. Okay, maybe? Not quite sure that this is fully correct. Okay, incrementally, so that removes some redundancy, and when you check or when you add things to the queue. So you have your list of deltas, you have your scene, studio array, with the heap. I think the heap is just the best way of doing this. I can't imagine there'd be a faster data structure for this, or a better data structure for this. In theory, maybe you can have a heap of a single tuple, a tuple of time, and then some single number that represents the row and column. Yeah, this is as I think elegant as it's going to get right now. If it's valid, I'm not seeing switch true. I mean, in theory, you can maybe do this check before you do the heap push. That might be ever so slightly faster. Yeah, negligible. Okay. Summary. So this is going to be. This is almost like similar to a kind of breadth first search, breadth first search graph graph traversal. So you're going to start with lowest cost node/room and add onto the heap the neighbor rooms and their costs. Neighbor rooms. This is going to be costs for a column. Tuple. Neighbors rooms tuple. It will allow access to the min cost room to explore each iteration of the loop. So any additional rooms added to the heap will be added, will be shown with the smallest time cost to get there, because you're always going to go for the kind of shortest time cost path. Time complexity, okay, and then there's use a set or 2D bool array to keep track of which rooms you have been explored, and don't go back over, or don't add same rooms that have been explored. So that's the scene thing here. It's a 2D array of false. If you haven't seen it, initially set to true because otherwise it wouldn't work. And then when you check for whether or not a room is valid to be added to the heap, it needs to be in bounds of rows and columns of the array, and secondly, it needs to have not already been seen. Anytime you use the one we've seen type data structures, you should immediately set it to true that spot after you have a condition but haven't seen it. And then I think that's it. And obviously, the most efficient way I've seen to traverse the rows and columns that are adjacent to, cardinally adjacent, or just adjacent to any kind of node. Northwest, east, south kind of deal is just have deltas and then do deltas on the do the delta row, delta column to find the next row, next column. Alright, and then time complexity, this is going to be O of this is O of n by m, where n is number of rows, n is number of columns, as all rooms can possibly be explored in the traversal. Yeah. N by m. Actually, there's a bit of sorting as well, because each time you do the heap, it sorts to find the lowest, and the cost of that is the size log times the size log of the size of the heap. So it might be n actually, and heap adding removal is log k, where k is size of heap. So I think this actually is going to become O of nm log nm. I guess this is set like that. I think that's correct. And then space complexity is going to be O of n times m, as heap can have actually yeah, it can have proportional, can have tuples proportional to the maximum number of rooms. I think that's correct. All right.